Good morning, class. Welcome to the second week. The last class we did this example 3, and before that we were looking at kind of energy balances and deriving equations depending on the process that we have. And it was kind of mainly a review, I would say, from what we've seen so far from Thermal 1. The equations that we kind of saw in the end were maybe a bit more derived than what we saw in Thermal 1, but it's the same basics, same starting points, and we're just going from there. Today we're going to continue with that and then go into equations of state that are for real systems instead of ideal, which is kind of what we focused on in the last class. So the last kind of thing that I want to talk about in terms of processes is this polytropic system or model, which basically shows us the relationship between pressure and volume for a given process. Okay, so polytropic means turning many ways. Okay, so it could be, constant volume, it could be constant temperature. So depending on the process that you have, the polytropic equation will represent what is the relationship during that process. All right. So PV relation, PV to the power of delta equals to a constant. So this is the polytropic.
I don't understand. Can you give an example?
So we're going to go through the examples. All right. So if delta equals 0, we have PV to the power of 0 equals to a constant. So that means any number to the power of 0 is 1, right? So then pressure equals to C, which is a constant. So that means it's an isobaric process. So from the general equation, we're looking at how, based on the delta value, we can get the different processes. If delta is an infinity, so PV to the infinity equals to a constant, C divided by V to the infinity, meaning a very big number, is equal to what? To 0. So from this, we can say that work is 0. Delta V is equal to 0. So isochoric process. From ideal gas, PV to the power of delta equals to a constant, we can also say that TV to the power of delta minus 1 is also a constant, or in terms of pressure and temperature. So we're only changing the variables here, combining either pressure and volume, temperature and volume, or temperature and pressure. And looking at how the power basically changes for the polytropic case. So if delta is equal to 1, we can take the second equation, right, and write for delta 1. So we have 1 minus 1. So now we have V to the power of 0, right? So now the V is 1. And then we say that the temperature is constant for that process. So isothermal process. Now if delta is equal to gamma equals to Cp over Cv, this is called the heat capacity ratio or specific heat ratio. Okay, so we use this power in PV delta when we have an adiabatic process. So when Q is equal to 0, then delta is equal to Cp over Cv. All right, and this was derived in last class, this Cp over Cv for this specific heat ratio. All right, so here we see the general equations, all right, for work and heat given a polytropic process. So let's say, if it was isobaric, then delta 0, you plug in 0 here, right? Everywhere you see a delta, you plug in 0. If it's infinity, you plug in infinity. If it's a 1, you plug in 1, and so on. So you can get the work and the heat for a given process using these generalized kind of equations, all right? So that's just kind of summarizing what's a polytropic process. And on this slide, we see a plot where we have pressure versus volume, and we can see each one of these cases specifically, right? Yes. Turning many ways. You can have many different processes, right? Each one of these is an example. Yeah, but they're all represented by this PV to the delta, and delta is a value depending on the process type. Different pathways. So the end result will be different depending on the path that you take. Okay? And if it's a constant volume, in that model, the PV relation, PV to the power of infinity. If it's adiabatic, we get the heat ratio. If it's to the 1, then it's isothermal. If it's 0, isobaric. It's a model, it's kind of like an equation that will tell me the function of pressure versus time, you can say, for that given process. Okay? So that we can, depending on what we're measuring. If volume is changing, then we can consider volume as step by step, right? So, but it's basically showing me the path that we're taking. All in one equation, we're only changing the power. Okay, it's just to simplify kind of the equations used to represent the PV relations. All right? So now we're going to move on to the equations of state. All right, the first one is the virial equation state, which you should have seen before. And these equations of state basically show us correlations between pressure, volume, and temperature. All right? So the virial equation state is derived based on statistical mechanics, and the general equation is that PV equals A plus B times P plus C times P squared, and so on. So it's a series where we're multiplying coefficients by pressure, and we keep increasing the power of that pressure as we add more values to that series. Now if we say that, let's say B, the second coefficient, is equal to A times B prime, and C is equal to A times C prime. So we're kind of using this initial coefficient A in the rest of the coefficients and changing them to primes. All right? So we can plug those in and we can factor out the A. So then we get PV equals A times this whole bracket. Right, so that's Z. And how do we know that? Because this A here for ideal gas is what? RT. No.
Oh, yeah, so this one.
Z is 1 if all these coefficients are 0. But this A here represents, if it's an ideal, it would represent RT. Okay? So that's what we see here. So from the equation Z equals PV over RT, if I move PV over A, or saying PV over RT, then we say this is, like you guys said, Z. So that's just basically what we see here. All right, so that's for the virial equation. So that's the form in terms of pressure, but we can also write it in terms of volume. How do we do that? We just basically use the ideal gas, right? We plug in. So B equals to B prime over A. A is RT. So we can say that B over V, right? I took this B divided by V, is B prime RT over V, which is B prime times pressure. So B over V, this is B divided by volume. B prime RT divided by V gives me what? So RT over V is pressure. So then this is equivalent to this. All right, that's just showing you how these two are the same thing. You can write Z in terms of pressures, you can write Z in terms of volumes. All right? So in general, all of these, so the first value here, number 1, is considered the first virial coefficient. The B is the second, the C is the third, and so on. Okay? And again, what is it trying to represent? These coefficients are showing us deviations from the ideal. Why do we say that? Because the first value we see here is 1, and then we have these added to the 1. 1 is ideal. Z equals 1 is ideal. As I deviate from that, so as the coefficients vary, that will cause me to go away from the ideal case. Now, if Z, right, is equal to 1, it's ideal. If Z is greater than 1, right, it basically tells me that we're going to have a greater pressure in my system compared to ideal. If I have a greater pressure, it's caused to the molecules repelling each other. If I have attraction, then the value of Z would be less than 1. Okay, so then those coefficients have more attraction between the molecules. It will cause a lower pressure overall in my system. Okay, if you remember, if I go back here, look at this. So we have PV equals A, 1 plus, and so on. If this here is large, and let's say the volume is held constant and everything is held constant, if this is greater than 1, then my pressure would be larger. If this is less than 1, the pressure is smaller. Molecules, when they're interacting, if they repel each other, we get higher pressure. So then Z would be greater than 1. And molecules, when they attract each other, we get lower pressure. So then Z would be less than 1. Okay? So those are just understanding how the Z value affects the intermolecular interactions that we have. All right. And then here, again, we kind of saw this before. B prime, what it is. C prime is what we see here. And D prime is what we see here. In general, okay, when we look at the experimental data that's been done and the data that's collected and so on, we typically only use two forms of this equation. 1 plus B over V or 1 plus B over V plus C over V squared. That means typically we only have the constants B and C reported. So if we look here for nitrogen specifically, here we have on the x-axis the temperature. So B and C are both functions of temperature. So the virial coefficients are a function of temperature. On the secondary y-axis, we have the values for C. On the primary y-axis, we have the values for B. And you can see how they vary with temperature. All right? So when there's 0, it's the ideal case. As you increase the temperature here, you can see them varying. Okay? So using the reported data, we can plug those to the virial equation and determine the relationships between my P, V, and T. All right? That's the whole reason we have the equations of state, to find the correlations between these values. Another one that you've seen before is the van der Waals equation. Okay, again, we have A as a coefficient and B as another one. This thing here accounts for attraction or attractive forces, and then this here accounts for the actual volume of the molecules that we have. Okay, and that is showing us how they deviate from the ideal case. Here we have kind of functions to find what A and B are in terms of the critical volume, critical pressure, and critical temperature. All right, remember that's the state when we don't have an ability to distinguish between the vapor and the liquid phases for a given material, the critical point. All right, we cannot see the difference between the liquid and the vapor phases. So it's quite interesting that these points can be used to find correlations to those coefficients to find the behavior of a material or a gas, right, using the van der Waals equation.
It's the most accurate, right?
No, this is not the most accurate. So van der Waals, from the ones we're seeing here, is the second least accurate. So you have ideal, then van der Waals, then virial, okay, and then we'll see a whole bunch after in the next slide to come. All right. So, and the reason or the way you derive this equation compared to this equation is by setting ZC to 3/8. Okay, so in the kind of derivation of these, they set the critical factor of Z to 3/8. That's how we kind of convert from this 27/6 to 3 and this 1/3 to 8. Okay, as I use what equation? PC VC equals ZC RTC. Okay, basically PV ZRT, but all at the critical points. And I assume for this model, it's a kind of a simplification that all material have a ZC of 3/8. Okay, so it's kind of like a simplification so that we can come up with equations for the various materials, all right, with the same equation, just varying the critical points. So that is the van der Waals equation. So around like the 1950s, they were trying to figure out a more generalized equation other than the van der Waals, okay? And they came up with this equation here, which is similar to the van der Waals. If simplified, right, some of these variables, if they equal 0, I will get the van der Waals. So this is a kind of a generic equation, okay, where we have epsilon and sigma being pure numbers. Okay, pure numbers as they are, you know, based on the model that I'm using, they could be, say, a 0 or a 1. Okay, they're just a pure number. They're not, you know, like based on the material that we're using. They're based on the model that we're using. And we'll see a table of those. Then we have A and B, which are material dependent. Okay, so these depend on the material that we're using. So we'll have to use tables for those. And then this equation, right, using PV equals ZRT, was transformed to solve for the Z factor. Okay, and they came up with this equation. We're not going to go through that derivation, but this is basically what they got. They got Z equals 1 plus beta minus Q times beta, and then we have Z minus beta up here, and Z plus epsilon beta times Z plus sigma beta. Now beta is equal to omega PR over TR, right? Where PR is reduced pressure, right? So reduced pressure meaning that it's a ratio between the pressure of your system divided by the critical pressure. Okay, so that's the reduced pressure. No, that's not heat. We'll see in a second what it is. It's not heat. All right, and then TR, same thing. That's a reduced temperature. And then omega is an actual constant that we will see based on the model that we're using. Okay, so it's a parameter. When they were trying to fit all the materials, they found that omega, given this model, this number works best, so then they put it in the table. We'll see it in a second. Q is equal to psi times alpha. Alpha is a function of reduced temperature and the acentric factor, okay, divided by omega TR. Looking at all this, there's a lot of variables. Okay, it might look like complex, but in the end, it's all in a table. We'll see that table in a second in this slide. So we have this table summarizing the equations of state. The first one here is van der Waals. Then we have Redlich, Kwong, so RK. Then we have Suave, Redlich, Kwong. So the guy who started it was RK. So he started that paper. He published this model. Then they started building on that model. So that's why they keep adding names. That's what we see here. And then we have the Peng-Robinson, the PR model from 1976. Okay, so that's the latest one. So in the van der Waals, in the equation that we saw, so this is the general equation for Z, we have beta and Q. Here we see what the values are of alpha given that the model that we're using. So in van der Waals, this alpha is simply 1. Okay, in Redlich-Kwong, it's the reduced temperature to the power of negative half, or negative 0.5, or basically 1 over the square root of the reduced temperature. Okay, and then SRK, we have a whole equation, which is what we see here, which is a function of the reduced temperature and the acentric factor. Where do we find these? In the tables. Okay, we'll show that in a second. And it's basically a function of the shape of the molecule. So the acentric factor, which is omega here, that's a function of the shape of the molecule. All right, and then the Peng-Robinson, PR, another function. This is the function for alpha. Okay, so alpha PR equals 1 plus so on, so on, so on. Okay. Then we have sigma, right? Sigma is right here. For van der Waals, it's a 0. For RK, it's a 1. For SRK, it's a 1. For PR, it's 1 plus square root of 2. Okay, again, you don't memorize these, you just take them from the table. Okay, next thing, epsilon. They're all 0 except for PR, 1 minus square root of 2. Omega, for van der Waals, 1 over 8. RK, 0.08664. SRK, same value. PR, slightly different. Okay, same thing, psi. And then here we see the value of the critical compressibility factor that is assumed for all materials given this model. So for van der Waals, like I said before, it's assumed to be 3 over 8, right? For RK, it's assumed 1 over 3, and so on. Z is not used in the equation. Okay, it's not anywhere in here. It's just telling you what it was assumed to be, given the specific models. All right, looking at table B.1, we see the acentric factor, omega, for different materials. We have the critical temperature, critical pressure, and critical volume. So this is basically all you're going to need, and it's in page 680 to 681 in the textbook, depending on the version that you have. Okay, so if you have a different edition, you can check the book and find this characteristics or characteristic properties of pure species. Okay, so find that in the textbook and you'll find these values. All right, so here we have an example. Okay, we want to calculate Z using the RK approach, okay, for CO2 gas at 325 Kelvin and 60 bar. Actually, one more thing I wanted to mention. So this equation in general is used for gases. There's another one that we're going to see that's used for liquids only. For gases, when I'm trying to solve this, initially, we assume Z to be equal to 1. Okay? So when I'm trying to solve this equation, we can see that Z exists on the left and right side, like you mentioned. So to initially solve this equation, we assume initially that Z equals 1. We plug it in, we find a new value for Z, then we iterate. Or you can use solver, but on an exam you can't use solver. You're going to have to use iterations to solve for Z. So now we go to the solution to find what the equation of state for CO2 is. We need to figure out what the acentric factor is, what's TC, what's PC, so we can plug it in to the equation. So we go to the table B.1, we find the values, we take those values, and then we take from table 3.1, which we saw earlier in the slides, what's the omega factor, what's the psi factor, what's sigma, and what's epsilon. For what? For the RK equation of state. So these are specific for RK. These are specific for the material that we're using. All right, so now we go on. Beta equals omega PR over TR. Q equals that. And we have TC value, PC value, VC, eccentric factor, right? We have sigma and epsilon. And we have this general equation, which is used for finding Z factor for a gas. So here we see that sigma is 1. So this sigma is going to be a 1. So here we're going to have Z plus beta. This epsilon is a 0. So we're going to have Z plus 0, right? So this would be just simply, let me just, I guess, skip some steps here. So it will be Z multiplied by Z plus beta, okay? Now solving for beta and Q, right? Omega is given from the table. PR we have to calculate, right? It's the pressure of my system, which was 60 bars, divided by the critical pressure, which we got from the table, 73.83. Reduced temperature, 325 was the temperature of my system. Critical temperature from the table, 304.2 Kelvin. Do the math, you get this value for beta. Same thing applies for Q. In this case, alpha is what? TR to the power of negative 0.5. Divided by TR, so this is basically, simplifying this, would be TR to the power of 1.5.
Doctor?
Yes?
Solving for Q, what's between the brackets?
This one?
Yeah.
This is, alpha is a function of TR and acentric factor. For RK, it's just this. Right? For SRK, it's a longer equation. For PR, it's a longer equation. So now we found beta, we found Q. Now we can plug it into this equation. In addition to, actually that's all you need to plug in, the Q and the betas. So that's what we see here. All right, so we plugged all those in. Now we want to solve for the equation. So initially we said for a gas, we're going to assume Z to be 1. So in this equation, we're going to write ZA on this side and ZC on this side. ZA is the assumed, ZC is the calculated. Okay? If you've done numerical methods, right, this is one of the methods that we use to solve equations. We move everything to one side, keep the x on one side, and then just take an initial guess for what x is, and then just iterate. and now we'll converge to the correct answer. All right, so that is what we're doing here. Initially, we said z is 1. And as we iterate, we want to check, how accurate am I getting? Right? So how do we do that? We check what's the value of zc compared to za. Divide by zcy, because the calculated z would be the more accurate value.
And then we plug ZC instead of ZA.
Right, and then in the next iteration, your zc from the last iteration will be your new za. So that's the new assumed value for z. Then you do another calculation, you find zc and so on. What's that? Yeah, right. So here we'll see the table. Initially, the assumed is 1. I do the math, I find that it's equal to 0.80786. Now, I'm taking this value and compare it to the 1. What's the difference using this equation? 23.78%. So quite a large jump. So that means the error in this value is going to be,
What's the accepted error?
depending on what we're going to say. Say if we say less than 1%, then you would stop at this point. If you say it's less than 0.1%, then you want to continue till you get to this iteration. So typically it'll be less than 1. Okay? So I will let you know if it's different. All right. But if you're doing work yourself, like at home, right, just on an Excel file, you can do this so fast, then you don't want to stop at 1%, okay? You'd want to get the most accurate value you can get if it was a project, okay? All right, so we've done the comparison. We found that it's high. So now we're going to take this to be my new assumed z factor. So I'm going to plug that in this equation at this point, and this point. Do the math again. Find the new calculated z factor, which is going to be 0.75640. Compare the two, I get 6.8%. And then continue. Okay, so you just keep doing this, taking the assumed, making it the calculated, until you drop to a point which is acceptable. So that's how you solve this z factor. And then once you have the z factor, then you can plug it into PV equals ZRT. And you can find, if you have the pressure and the temperature, then you can find the volume of your system, which is the case here, right? We have the pressure, 60 bars. We have the temperature, 325 Kelvin. So then, from PV equals ZRT, I can rearrange. Now I have my Z value, I have pressure, I have temperature. We can solve for the volume of the gas, right? So that's simply what we're doing here with these equations of state. So I posted, so this is the last slide, okay? The last slide is the question slide, okay, if you have any questions. But I posted on Blackboard a PowerPoint of, you could say, practice problems that are homework, you can say, but you can work on them now, okay? So we have about 20 minutes, okay? I did post them, and they are like a PDF. And let me just open them up here.
5 questions.
5 questions, yeah. They're right here. All right. So because in this course we don't have homework, okay, we don't have assignments, this is your practice, okay, for topic 1, okay? So in the first problem here, you want to calculate the pressure exerted by a certain number of moles, okay, using the Virial equation of state, given the value of B, right, at 273 Kelvin is this. Okay, so that's one of the second coefficient, Virial coefficient. In problem 2, again, Virial equation, just different values and different givens. Then we have the third problem. You want to use the SRK equation of state. So kind of what we covered today. You go back to the tables, you find, what's the omega value and so on, calculate the Q, calculate the beta, plug it in, find the Z value, and then you can find the volume after that. All right. And then the last problem, or not last one, so there's another problem with SRK. And then we have this problem, which is more related to the equations that we saw earlier about work and so on. So if you do some work, you find that you get a different answer, review it, try to see where you went wrong, and then if you need any help, send me an email or come to the office hour and I can help you with that. Okay.